Hi everyone. Today we like to present our group project, which is on development and simulation of turbine applications on Malaysian rivers. Okay, so let's get into our presentation. Development and simulation of turbine application on Malaysian rivers within a focus on Bentong River. We designed a Pelton water turbine to harness the river's hydrokinetic energy. Given the high head and low flow condition of the river like Bentong River, a Pelton turbine efficiently convert water flow into a mechanical energy. Okay, first, the Bentong rivers are locational within the city, make it ideal for local power generation. By developing this system, we reduce Bentong depends on the national grid, integrating the electricity seamlessly into a local network and minimizing the losses. Next, uh, this project offer economic and environmental benefit by attracting business, boosting local employment, and reducing carbon emission through a clean hydropower, aligning with the Malaysian climate goals. And next is the it also provide educational opportunity for students and affordable energy for the community, enhancing resilience and reduce costs. Our project demonstrate the potential of suitable hydropower solution in Malaysia.
Good morning. My name is Tavanishan Palan. Let's dive into the fluid dynamic calculation for our Pelton wheel turbine. So we have used following parameters like jet diameter is 33 mm, the height is 40 meters, for the flow rate 0.3 cubic meter per second, and we also assume the efficiency will be 85 percentage, which is standard for our Pelton wheel turbine. So firstly, we calculated the power output by using the formula efficiency times with density times with gravity with head and flow rate, and by substituting our values we calculated the power output will be 100 kilowatts. This will represent the mechanical energy available to drive to the generator. So secondly, we calculated the jet velocity using the formula vjet equal to square root of 2gh, where we calculated the jet velocity as 28 meter per second. For lastly, we calculated the torque using the torque equals to power times with omega, where we assume the rotational speed of omega is 50 radian per second. So the torque is around 2000.36 newton meter, and ensuring the sufficient rotational force to the system. And after that, we calculate the energy production for the household supply, where the power will times with 24 hours a day times with 365 days. So it will show around 800,776.175.2 kilowatt per year, and we can supply to 244 household per year. And this is our turbine design, where we use SolidWorks to create our Pelton wheel turbine. And for the materials, for the runner which holds the buckets and rotates to the transfer energy is made from stainless steel, because this material offers excellent strength and corrosion resistance. For the buckets, it's made from Martin static stainless steel. This material provides superior wear resistance and toughness, ensuring the minimal degradation over time. For the nozzle, we use hardened stainless steel. This material resists erosion and maintain its precision shape. For the shaft and bearings, we use high carbon steel, and for its high tensile strength and resistant to fatigue. For the bearings, we use Teflon to reduce friction and to support the shaft. For the casing, we use mild steel, and because this material is cost effective and sturdy and capable of withstanding general wear and flow. Mechanism of the Pelton wheel turbine. So firstly, the water will flow from the high elevation through the pressurized pipeline, where it's directed into the split jet by a nozzle. So this jet strike a splitter of each bucket, dividing the water into two streams. The curved bucket deflect the water by under 65 degrees and transferring the water kinetic energy to the runner. So the runner rotates due to the impulse, and the rotational energy is transmitted to the shaft to drive a generator to produce the electricity. So finally, the used water exit the turbine, is returned to the water, and it will complete the cycle.
Hello, my name is Divyendrash and my metric number is MA23166. So for this section, I will discuss the simulation objective and the model preparation for our Pelton turbine project using NCs. So the primary goals were to evaluate the turbine performance by analyzing key factors like efficiency, power output, and torque. To study fluid structure interaction, particularly how water jets impact the turbine buckets. So to achieve these goals, we started by designing a precise 3D model of turbine in SolidWorks. This included key components like runner, buckets, and nozzle. Once completed, the model was exported as a step file to preserve dimensional accuracy and then imported into the NC's workbench. In the pre-processing phase, we checked for gaps, overlaps, and unnecessary details in the geometry to reduce computational load while maintaining accuracy. Critical areas such as the inlet, outlet, and walls were labeled using name selections, making it easier to apply boundary condition during the simulation. So next, let's move on to the mesh generation and simulation setup. For meshing, we used a tethered mesh with inflation layers to handle the turbine's complex geometry and accurately capture boundary layer effects. Refinement was applied in critical areas such as bucket edges, jet impact zones, and near the nozzle to ensure accuracy. Key quality metrics were maintained, including an aspect ratio below 5 and a skewness of 0.85, ensuring numerical stability. This approach provides a good balance between simulation accuracy and computational efficiency. After meshing is done, the model was set up in ANSYS Fluent. Boundary conditions were applied as follows. The velocity for the inlet was 28 meter per second. The outlet was set to atmospheric pressure, and the no slip condition were used on the turbine walls to account for frictional effects. The fluid properties of the water were defined with a density of 1000 kg per cubic meter and a viscosity of 0.001 Pascal per second. Finally, let's look at the simulation results. The turbine reached its maximum efficiency of 88% at a rotational speed of 60 radians per second, with a corresponding torque of 2400 Newton meter. Beyond this speed, efficiency began to decline slightly due to the turbulence of low inefficiency. By plotting efficiency and torque against rotational speed, we observe that the turbine operates best within a specific speed range, confirming our design suitability for high-head, low-flow application like the Bentong River. To summarize, the simulation results validated the turbine design, showing strong alignment with theoretical expectations. The incited gains from the study, such as optimal operational speed and performance trends, will be invaluable for real-world implementation and further design improvements.
Okay, so lastly, I'd like to discuss the evolution of our simulation result. First, let's look at our simulation outcome. Our Pelton turbine achieved the highest efficiency at 88% and is operating at a rotational speed of 60 radian per second, with its corresponding maximum torque of 2400 Newton meter. This result indicate the turbine perform optimally within the operation range. Moving on to the design optimization, this result suggests that a further fine-tuning is needed to improve the performance at higher speed. This includes the adjusting the bucket design to minimize the turbulence and refining the nozzle geometry to ensure more uniform water-jet impact. Additionally, a selecting material with a higher corrosion resistance will enhance the turbine's durability and reduce maintenance costs. Next, in the term of energy generation, our simulation estimate an annual energy output of 876,175.2 kilowatt. This amount electricity can supply around 243 households, significantly contribute to the local energy needs of the Bentong. And finally, let's discuss on the impact on the community and industry. The electricity generated by this project will reduce the community dependence on the national grid, providing a stable and a reliable power source for the both household and local factories. The stable supply can support the industry operation and attract new business and promote economic growth in the region. In the conclusion, the evolution of highlight the Pelton turbine potentially to meet Bentong energy demands, sustainability, and support the area's economically development.